Let's suppose that a board with mass m with uniform mass acts as a seesaw for two people as shown. So we have the following board that has uniform mass and has a mass of 3 kilograms. And we have two people on each side of the board, on each end of the board, that are standing. So we have person number 1 with mass 70 kilograms, M1, that is found in distance x1 from the pivot, from the point about which our board rotates. And x1 is given by 3 meters. Now we have person number 2 with mass M2, which has a value of 50 kilograms, and that person is standing some unknown distance x2 from the pivot. Assuming that the board is in static equilibrium, so it's not rotating and it's not translating, we want to calculate what our x2 value is. Let's begin by recalling that for an object or system of objects to be in equilibrium, well, what that basically means is the net torque and the net force acting on our objects is 0. The sum of all the forces and the sum of all the torques is equal to 0 along any axis or about any axis. So let's begin by drawing our force diagram for our board. So the board is the object we're examining, and because we assume our mass m is uniform of the board, that means the center of mass where gravity acts, where the force of gravity acts, is right in the middle. It's at the pivot. So this is our pivot. We have the force of gravity pulling downward on the board, and the normal force created by this triangle holding the board points upward in the opposite direction. And now we have the two forces, force F1 due to person 1 and force F2 due to person 2. And they both point downward. So if we sum up all the forces acting on our board along the y-axis, we see that the sum is equal to 0. So we choose going upward to be positive, downward to be negative. So we have the normal force minus all these 3 forces. And if we wanted to, we could solve for the normal force by using the following equation. We simply bring all the negative forces to the right side and solve for the normal force. Now, let's go to step 2. We actually don't need to use this information to solve our problem. What we do need to use is torque. So we said not only is the net force along any axis 0, but the net torque about an axis is also 0. The net torque acting about our pivot, about this position, is equal to, well, the sum of the two torques created by these two forces. Notice that the lever arm for the normal force and the force of gravity is 0, so the torques created by these two forces about this point is also 0. So we only have these two forces, so we only have these two torques. So torque 1 is positive because torque 1 points in the counterclockwise direction, and we choose counterclockwise to be positive and clockwise to be negative. So we have torque 1 due to force 1 minus torque 2 due to force 2 is equal to 0. So we bring torque 2 to the right side, and we see that torque 1 has to be equal to torque 2 in order for our board to be in static equilibrium. So let's plug in force 1 multiplied by the lever arm x1 is equal to force 2 multiplied by the lever 2 x2. So since we want to know what x2 is, we have to solve for x2, and we get the following equation. F1 multiplied by x1 divided by F2. Now notice F1 is simply M1 multiplied by G. And F2 is simply M2 multiplied by G. It's the force of gravity acting on our two people. Now notice G's are constants, so we can cross them out. We get the following result. So now we plug in M1, which is 70 kilograms, M2, which is 50 kilograms, and X1, which is 3 meters. We plug those quantities in, and we get that X2 is 4.2 meters. In other words, for this entire system of objects to be in static equilibrium, this distance x2 has to be 4.2 meters. So it's longer than distance x1, and that makes sense because person 1 has a higher mass than person 2.